Hello. So this is my talk on the structure of stable codimension 1 integral varifolds near classical cones of density 5/2. My name is Paul Minter, and as I said in my intro video, I'm a current PhD student at the University of Cambridge, and I work on these regularity problems for minimal surface theory. So I wanted to split my talk into two bits. So the first part is going to be focused on just the setup and sort of some of the background for the talk. And so I'm going to be giving statements of some known theorems and some examples to illustrate the difficulties that can arise when we study regularity problems for minimal surfaces. And then the second talk is going to be focused on the details of the actual work in this setting. So I hope this talk will give some context to the problem and to sort of motivate the ideas, or where they come from at least. So yes, so in regularity for stationary, for minimal surface theory, we want to study objects known as stationary integral varifolds. So a stationary integral varifold is essentially a weak form of a minimal surface, which, just like with Sobolev spaces for PDE theory, we have to work in a suitable generalized class of functions or surfaces so that we have suitable compactness properties as we want to be able to take limits and things. And so when we're working with surfaces, especially when we're talking about things like area, a natural way of doing this is to work with measures instead of functions and smooth manifolds and things. So in this setting, so a varifold, just sort of very quickly, will be a radon measure on some Grassmannian bundle over an open subset of, say, Rn. For everything, we're just going to work in Rn, at least for this talk. So this is a radon measure on some open subset of Rn. And then we take the Grassmannian bundle. So this is n-dimensional planes in Rn plus K. Sorry, this should be Rn plus K, an open subset of Rn plus K. So, and so this is an n-dimensional varifold because we're looking at n-dimensional tangent planes in R to the n plus K. And so what this tells us is the measure on the U part will tell us which points in the space are in our varifold. And the measure on the Grassmannian part will tell us which tangent plane we're looking at, essentially, for a given point, what tangent plane is there. So it's a tangent property. And because this has to be defined almost everywhere, with respect to Lebesgue measure, we are allowed to have points where there isn't a tangent plane, which will be what our singularities are. The integrality assumption is an assumption on the measure, essentially that the measure at every point, the density of the measure, is integer almost everywhere. So this essentially just means integer measure. So the density is integer almost everywhere. And then the stationarity is where the minimality for a minimal surface comes in. And this is the usual first variation of area. It vanishes. Just write that again because it's very small. First variation of area vanishes. And so some examples to illustrate what we mean. Any smooth minimal surface is going to define a stationary integral varifold just via taking the usual surface and the tangent planes. So we get things like catenoids, Shirk surfaces, planes, helicoids. So we get all the sort of usual minimal surfaces. But we also get more general non-smooth objects. And an example of this is what we will call a triple junction. So something that looks like 3 planes meeting along an axis. So this is no longer a smooth minimal surface, as every point along this axis will be a singularity because it's not locally smooth. So this is what we'll call a triple junction. Again, there's some stationarity condition that has to be satisfied between the angles, and it turns out that the angle between each half plane has to be 120 degrees for this in order to satisfy the stationarity condition. Okay, so when we work with these stationary uniform varifolds, like we said, we want nice compactness properties. The additional issue, which is compounded here, is that when working with measures, it's possible for us to get higher multiplicities in the limits of our surfaces. So to illustrate this, if you just take a very simple example of 2 lines, which are some distance epsilon apart, as we take epsilon to 0, this will limit onto a plane, but now it's going to have double the mass because we're taking the measure in a region. So if we take a look at the measure in this region, the measure is going to be conversion to twice the measure of the line. So what we end up with is a very thick line, or just multiplicity 2, so double the multiplicity. And so when this happens, when we get high multiplicity in limit objects, this is where a lot of the difficulty comes in understanding the singular structure of minimal surfaces. And this very much does happen. There have been constructed examples where you do have high multiplicity singular points. So it's very much a known problem. So the question is, what can be said in these scenarios? So the basic question we're going to be looking at is what can be said about the local structure of V, a stationary integral varifold, about a singular point. So what we do know, and this is a sort of a well-known result, is that we can at every singular point we can produce tangent objects, just like for a smooth plane or a smooth submanifold, we can produce tangent planes. In the measure sense, we can produce measure theoretic limits via taking a point and rescaling the varifold at the point. And the resulting object is what we call a tangent cone. So a tangent cone is a limit of the form C is the limit. This is as varifolds now, so as random measures, as say j goes to infinity of some. So we take a point, we translate, and we rescale by some sequence rho j, which these are positive numbers that go to 0. Of course, I haven't defined explicitly what I mean by this translation rescaling, but this is essentially the idea that I take, say, any smooth thing, just like in this setting, I take any point, and if I zoom in at the point, what does it look like? I'm going to look more and more flat, so I get a plane in the limit in this smooth setting. The issue is that when we've applied this compactness theorem, we have to pass to a subsequence in order to get the limit. So there's another big open question, which is the uniqueness of tangent cones question, which is just, is C, this tangent cone, independent of the choice of rho j the choice of sequence that goes to 0. For every sequence going to 0, we know we can find a convergent subsequence, but we do not know if C is independent of the subsequence itself. What we do know about C is that it is a cone in a sense of its scale invariant about the origin. So C is a cone, and so it will look like, so we know C is a cone, which is a stationary integral varifold. These are some well-known compactness theorems that can be found in Leon Simon's book on geometric measure theory. So it is a stationary integral varifold, which is a cone. And by a cone, I basically just mean that if I multiply C by some constant, I get C back. So it's scale invariant. Okay, so at any singular point, we know we can produce these tangent objects, tangent cones. And so a natural way to study the local behavior about a singularity would be asked the question to look at certain varifolds which are close to these stationary integral cones now. So we want to fix a cone and look at varifolds which are sufficiently close to it and see if we can say anything. Of course, you don't have to tackle this question this way. The uniqueness question is more general, but if you want to understand the local singular structure, this is one way to go about it. And so two of the most famous results in this direction are a result from Allard in 1973 and a result from Leon Simon in 1993. I believe Allard might be 1972. So we have these two results, which are very well known because they hold in complete generality without any further assumptions in any dimension in codimension. So we have result 1, which is Allard, 1970, I think it is 1972 actually, which is that if a stationary integral varifold this is any dimensional codimension, is close as varifolds, and by that we mean in Hausdorff distance of the supports, as well as the mass. So the mass and the Hausdorff distance of the weight measure. So just looking at the points in the space to a plane of multiplicity 1. So the mass is going to be close to 1. Well, the density mass is going to be close to just multiplicity 1. Then, in fact, let's call this variable V. In fact, V is smooth. And moreover, it's actually given by a smooth graph over the plane we are close to. So what this tells us is that if we ever take a point in a varifold, and when we rescale, we end up with a limit which is a multiplicity 1 plane. Allard actually tells us that in fact, that at that point is not a singular point, it must be a regular point. So that's a very useful fact. So we cannot have singular points that have a tangent plane of multiplicity 1. The other result, this is from Leon Simon in 1993, his cylindrical tangent cones paper. In the same setup, so we have a stationary integral varifold, it's close as varifolds. Now it's close to a triple junction. Again, multiplicity 1, I'm going to sort of make it implicit. So it's multiplicity 1 triple junction, just as we drew above. Then V is in fact a C1 alpha perturbation or graph of the triple junction. So what I mean by this is that if I have a triple junction, let's just look at the cross section. So something like this. If I'm sufficiently close to this, then I have to be able to find along the singular axis of the cone, I can find a graph over the singular axis, which defines the singularities of V. Maybe it's better if I actually draw a two-dimensional picture to make it clearer. So we have a triple junction. And so, okay, so there's a function over the spine, it's called, so the singular axis of the cone, which defines all of the singularities in V. And then there's graphs over the planes, which glue together V over each plane. So we get something that looks like a triple junction, but is slightly curved. So V, if we're close to a triple junction, V must be actually a perturbation of it. And in fact, the C1 alpha regularity can be upgraded by a result from Brian Krummel to smooth. Okay, so what this tells us again is that if we have a tangent cone, which is a multiplicity 1 triple junction, then in fact, the Varifold itself must also look like the triple junction locally, and there's no other interesting behavior. So it does, tangent cone does in fact model V itself. So these are the two sort of so-called epsilon regularity results known in complete generality for stationary integral Varifolds in any dimension in Codimension. What we also know is a sort of a stratification of the singular set from Almgren. And this is in Almgren's big regularity paper. So this is a stratification of the singular set And what this tells us is that, again, in full generality, the singular set of V of the stationary integral Varifold can be decomposed in the following way. It can be decomposed into three sets. This K has dimension at most n-2, so it's dimension 2, it's small. This B is called the branch set. And this is all the singular points, where a tangent cone is a multiplicity, a plane of some multiplicity. Now, it turns out from something called the constancy theorem that multiplicity has to be constant across the Varifold, across the tangent plane. So therefore, as these are integral Varifolds, there has to be some integer density. So we can sort of further split B up into singular points where the tangent plane is of some fixed integer density, positive integer density. And we also know by Allard that the Allard regularity theorem that it can't have a singular point where a tangent plane is multiplicity 1, and thus we know that the multiplicity of the plane must be in sort of 2, 3, 4 or more. And finally, the S set is the singular points where a tangent cone is of the form C is sum C0 cross Rn minus 1. So this C0 is a one-dimensional cone in the resulting ambient in R1 plus K for Codimension K minimal surface or stationary integral Varifold. And so in particular, because it's a cone, C must actually look like a union of rays. We don't know how many rays, but a union of rays. And so you can actually see then by thinking about how much mass contribution each ray or half line contributes to the mass of the origin, that sort of the density at the origin of C0 is in 3/2, 2, 5/2, 3, etc. So half integer, because each half line corresponds to sort of half the mass to the origin. And again, we understand from Simon's result above, if C0 has density 3/2, i.e. it's comprised of 3 half lines, then the singularity then has to be a triple junction singularity. And so we understand the local structure of V. So the only part of the singular set which can be like sufficiently high dimensional, so n-1 or bigger than n-2, are the singular points which lie in B and S. So for that reason, we call, for the purposes of this talk at least, the top dimensional part we'll call it sing top of V is equal to the B union S. And so if we want to understand the sort of quote majority of singularities, we want to understand singularities in B and S. And we have a nice characterization as we've got above of the densities. Sort of in the case of B, they have to be integer density. And in the case of S, they have to be half integer density. We have a nice sort of way of working. So I guess inductively in some sense. So the first unknown case, given the two results above, is when either we've got a multiplicity 2 tangent plane or a multiplicity 2 cone of the above form. So S, I should add that obviously we don't want elements of S to have a tangent plane, which is a multiplicity 2 or higher plane. So we're ruling out those tangent cones for points in S. So, and you can check so now in the codimension 1 case, we'll forget about codimensions bigger than 1 now, so we'll just take K as 1. Things get more complicated if K is bigger than 1. What we're after is tangent cones. We have 2 situations in the next setting, which is where we have a tangent cone, which is a plane of multiplicity 2, or it's 4 half planes, half hyperplanes, I guess now, meeting along a common axis. And it can be readily checked from the stationarity condition that they actually have to form 2 lines, all of multiplicity 1. So we now want to understand varifolds, which are close to multiplicity 2 planes or a union of 2 multiplicity 1 planes. Now, you can ask if in this full generality, whether we can hope to prove such a theorem. And unfortunately, there are simple examples to prove that we cannot. So for example, for a multiplicity 2 plane, we can take actually rescalings of a catenoid. So if we look at rescalings of a catenoid, they become very, very flat, but there's still this hole in the middle. And this hole means that whilst we can be maybe arbitrarily close as varifolds to a multiplicity 2 plane, we're never going to be able to express a general varifold close to a multiplicity 2 plane as a graph or a suitable graph, because there's going to be a gap in the middle. And in the case of 2 hyperplanes in multiplicity 1, there's also another simple example that can illustrate that we can't necessarily always express a nearby varifold as a sum of 2 graphs over each plane. And that's just via, if we take one of the planes And now we insert a triple junction, and then we have another triple junction where it goes off. By making the little segment in between very, very small, this will come arbitrarily close to a union of sum of two planes, but it's never going to be a graph, a sum of two graphs, because of that segment in the middle, which is only multiplicity 1. So we have no hope of proving the complete analog of the above results in this setting, because we have these examples. However, we can look at these examples and work out what potentially goes wrong. In the second case, we have these triple junction singularities, and we know that a triple junction, just from its structure, will never be able to be expressed as two graphs, a sum of two graphs. And so if we hope to understand these objects, we have to have some assumption that rules out these triple junctions nearby, these triple junction singularities, or just somehow rule them out a priori, which this example should be called, without more assumptions. In the other case, which everything's completely smooth, although what we do have is a region of very high curvature, where the varifold very rapidly changes direction. And so some sort of curvature assumption or curvature control would potentially rule out this situation. And so far we've just been considering stationary integral varifolds. But if we add in this assumption of stability, which is when the second variation is also non-negative, second variation of area, that is non-negative, then the resulting inequality can actually be, in codimension 1, can be shown to give an integral bound on the second fundamental form, so the curvature of the norm of the second fundamental form. So we get some control of the curvature, and it turns out that if we assume stability and that there are no triple junction singularities, we can actually start to prove regularity results like above in this setting. This was originally done by Nishan Wickramasekara, my PhD supervisor. The work hasn't been published yet, but it's going to appear in a joint work, a more general joint work between myself and Nishan very shortly, hopefully over the weekend or the next couple of days. It should be on archive. And so yes, what we need, what the next setting in stable codimension 1, we can prove the following. So the following theorem. So this was originally done by Nishan Wickramasekara, but it's going to appear in Minter Wickramasekara for the first time in published form, at least. Nishan has given talks on this himself, 2021. So again, if V is stable, so again, this just means that the second variation essentially just means the second variation is non-negative. Codimension 1, integral varifold, in some set. So we're going to look at a cylindrical region, and such that V has no triple junction singularities. So the stability assumption is just on the regular part. It turns out that that's all that is needed for Nishan's work. So in this setting, then we have the two following results. That there exists an epsilon 1, it only depends on the dimension, such that if V is epsilon 1 close to the multiplicity 2 plane, Rn 0 cross Rn, this is just an notation for the associated varifold. Then, in fact, we have that V on a smaller set is equal to is a graph. And this function u is defined over the smaller set. And the thing is, it's not a single valued graph, it's a two valued graph. And this is the notation. Curly a of sub 2 means two valued function. And there's many resources on two valued functions. So I won't go into the details of what this means. But the point is that it allows certain types of singular behavior which we do see in Varifolds, and examples have been constructed. And the regularity it's a C1.5 function, and you can't do any better than that. That is the optimal regularity. Two valued, I should say. Two valued function. And the second result is that if we have a cone, which is the sum of two hyperplanes, then there exists another epsilon, which now depends on the cone, such that if V is epsilon too close in the same set to C, then again, the restriction of V, the measure to the smaller ball, is in fact equal to a sum of two graphs. Where these functions are defined over the respective planes. So one over each hyperplane. So it turns out that actually in the second case, the B set, the branch set is empty. There are no branch points in this case. And in the first case, it's been shown that under the assumption of, well, if we look at stationary integral varifolds, which are described via C1 alpha two valued functions, then the branch set is actually n-2 rectifiable, countably rectifiable. And the dimension bound, the fact that it's at most n-2 dimensional, was originally established by Leon Simon and Nishan Ruckman-Zekera, and the rectifiability has been established by Brian Krummel and Nishan. Again, this is a work which is currently almost finished and should be published at some point soon. And like I said, this theorem is a special case actually of a more general theorem, which will appear in this paper by myself and Nishan very shortly. So what this tells us is that in the stable codimension 1 setting, if we rule out triple junction singularities, we understand if I just scroll back up, we understand the top dimensional part of the singular set, where for singular points, whether we have a tangent cone, which is a multiplicity 2 plane, or a sum of two planes, hyperplanes. So the next case you can think about, the next sort of smallest multiplicity case you can think about is the case of singular points in S, where the density is 5 halves, or they're formed from 5 half hyperplanes. Now that is the setting which is one I'm going to be discussing in the next talk in detail. And so my paper analyzes this next case and is able to prove a regularity result under the same assumptions. So the theorem, so the main theorem I was able to establish. So this is by me back in August, is that if we have a cone of the form C0 cross Rn minus 1, a stationary integral cone, integral n-dimensional cone in Rn plus 1 with, well, comprised of 5 half lines formed from 5 half hyperplanes, I'll say. Then there exists an epsilon, which only depends on C, such that if V is stable, Codimension 1, integral Varifold with no points of density 5, no triple junction singularities, with no triple junction. Let's say triple junctions. If V is epsilon close to C, then just like in the triple junction case, we get that V has to be a C1 alpha perturbation of the cone, except now on any place in the cone, I'll draw examples in a second, any half plane in the cone, C, which has multiplicity 2, we have to have a 2-valued function, just like in Nishan's result. So then we can express V on a smaller set as a C1 a half multi-valued function over C. And moreover, all these tangent cones are unique. So we answered the uniqueness of tangent cones question for this type of tangent cone under these assumptions. And the points of density 5 halves form an n-1 dimensional C1 alpha submanifold. So just like in the triple junction case, all the singularities were perturbation of the singularities of the triple junction. The same thing happens in this setting. So what different types of cones can we have in this setting? So C is comprised of 5 half hyperplanes. And so that corresponds to C0, which is a one-dimensional cone having 5 half lines. So there are numerous different cases we can have. So C0 can take different forms. And so there are 3 different cases, which I refer to as different levels in the paper at least. So the first case is called level 0. And it's when the cone C0 comprises of 5 multiplicity 1 half lines. So all these multiplicities are 1, so we do have 5 distinct half lines. The next case, which I call level 1, is when we have 1 multiplicity 2 half line and 3 multiplicity 1 half lines. And the final case, level 2, is when we have 2 multiplicity 2 half lines. So we have 1 multiplicity 1 and then 2 multiplicity 2. It looks a bit like a triple junction, but the angles aren't all symmetric as in that. So we want to study varifolds of the above form, which are of this form, which are close to cones of this form. And the point is that the you can have cones of level 0 that degenerate onto cones that are level 1 or even level 2. So that adds an additional level of complexity when you study level 1 cones or level 2 cones. Similarly, in the level 2 case, you can have level 1 cones that degenerate onto a level 2 cone, which adds a 2-fold level of complexity onto the level 2 cones. So again, the whole assumption of ruling out triple junctions in the varifold is a completely necessary assumption, because we can have other examples. We can have examples which are very close to these but aren't of that form. So for example, or where the conclusions don't hold, at least in this form. Some of the level 0 cones and some of the level 1 cones are actually decomposable, in the sense that they're actually a sum of a triple junction with a plane. And so yeah, we can have something like this, multiplicity 2. And in this setting, we can have nearby stationary integral varifolds that have points of density 3/2, and even stable ones as well, stable regular paths. And this can be seen just by, say, translating the plane or rotating the plane in either of these settings into something else. So we can get, e.g., something like this, or if we rotate in a different direction, we can get something that looks like a triple junction, but now we've rotated one of the planes, and so we get a picture like this, where if we rotate that plane back around, we can get arbitrarily close to a level 1 cone. And the thing is, in all of these examples, we actually have points of density 3/2 nearby. So in some sense, the ruling out density 3/2 triple junctions stops these examples from occurring in what we want. And so in fact, we can actually prove that there are no sort of gaps, density gaps that are so called, where the symmetries of the cone, so we have like this n-1 dimensional set of points of density 5/2, that is reflected in turn in the varifold. So so to prove this theorem, we're going to use a blow-up argument, which I'll describe in the next talk. And the main difference now is that when we blow up, we have the regularity results of Nishan that we can use over each of the half planes in the cone. But when we blow up, we know we'll have a 2-valued function over each half plane, or a single-valued function. But we need to establish regularity along the boundary at the boundary along these points very close by. We don't have any boundary regularity for 2-valued harmonic functions. And so we need to somehow establish a boundary regularity theory for 2-valued functions or harmonic functions. And that's going to involve proving properties of this so-called blow-up class, these functions that we gain when we perform this linearization. And we've proven several properties, and following an argument that's similar to one seen in Nishan's, Wigram-Mazekara's stability paper, his annals paper. So we'll describe that next time. Thank you very much for listening, and see you in the next talk.